At example 4. This one states find the limit of n over n plus 1 as n approaches infinity, and this is the one that we've been dealing with quite a bit earlier above. So what we'll notice first is, now that we know the limit definitions, we can solve this. So we know that, well, first of all, right here, if we plug an infinity inside this, or a large number, we're going to get an infinity over infinity, and this is not defined. So not defined. So what we can do is we could write limit as n approaches infinity as of n plus 1, and we can multiply the top and bottom by the, or divide it out by the highest power, which is n right here. So 1 over n over 1 over n. So then this would cancel with there. So we get limit as n approaches infinity. We're going to have, well, 1. Then the bottom here is going to cancel. We're going to have 1 plus n over there. 1 divided by n over there. 1 plus 1 over n. Now this just equals 2. Well, now we can use the limit laws. This could just go now. This becomes, well, 1 over 1 plus limit as n approaches infinity. Just for completeness sake, put it like that. So in other words, this bottom part right here approaches, well, 1 over infinity, which approaches 0. So put that like that. This approaches 0. Yeah, so it's approaching 0 there. So we get a 1 over 1 plus 0. In other words, we get a 1. And we just proved it. And now note that this is the same limit we looked at earlier in this video, as I stated, but this time evaluated directly to prove that it is indeed equal to 1, instead of just doing the indirect methods before. Nonetheless, let's go further and look at example 5 right now. When this one says calculate limit as n approaches infinity of ln n over n. So first thing to note again is, well, ln of infinity is infinity, and divided by infinity, again we have an infinity over infinity. This is not defined, and it isn't written in a simple way like the one above here that we could just divide by the highest power on top and bottom. But so we can look at L'Hopital's rule. Yeah, so we can look at L'Hopital's rule, but we can't apply directly. So note, we can't apply L'Hopital's rule directly since it applies to functions of a real variable and not to sequences. But we can do a workaround and then apply Theorem 1 relating the limits of functions to sequences. So remember Theorem 1, also recall L'Hopital's rule is just if you have an undefined like this, we could take the limit of the derivatives of the top and bottom, and they are the same as the derivative of the regular functions. So let's just write this as a function instead of dealing with sequences, because L'Hopital's rule is not defined for sequences. It's defined for real variables and not integers. But nonetheless, we can do a workaround. So limit as x approaches, so move that as a function, x approaches infinity of ln x over x. Now applying L'Hopital's rule, this equals to limit as x approaches infinity of the derivative. So ln x over dx, d ln x over dx, and then d over dx of x, so the derivative of top and bottom. And now if we take the derivative, recall the derivative of ln x is just 1 over x, and the derivative of x is just 1. So we just get, we get a 1 over x. So let's write this limit down. So this becomes 1 over x over 1. So in other words, we get, well, just 1 over x. So then if you apply infinity over, so then this becomes, again, 1 over infinity approaches 0. So this becomes 0, like that. Yeah, so thus by Theorem 1, what we end up having is just Theorem 1, because that's just a function, and then we just convert it into a sequence. The limits are the same. So limit as n approaches infinity of ln n over n equals to, it just equals to the limit as x approaches infinity of ln x over x. So this is a real function. That's a sequence. And this both equal to 0 because this equals to 0. So yes, very interesting. Yes, so now let's look at another example. Example 6. And it states determine whether the sequence an equals minus 1 to the power of n is convergent or divergent. So, well, first thing we should note is, well, we could write the sequence out. An is equal to, and write all the terms. You could see that it's going to be alternating. So when n is 1, that's going to be the first term. So negative 1 to the power of 1 is just negative 1. negative 1 to the power of 2 is just, well, positive 1. So we end up getting a negative 1, 1, and then the 3 is odd, so it's going to be negative. Power of 4 is even, so we get a positive. So again, it just goes like that, and it keeps going on, and so on. So it just alternates between 1 and negative 1. So if you were to graph this out, what you end up having is something looks like this. This is n, this is an, and we have a 1, and we have a negative 1 across here. So for 1, we have negative 1. For 2, we have 1, positive 1. And for 3, we have negative 1. And then for 4, we have positive 1 across here, and then as so on, so forth. Keeps going on and on. We just get like this, and like that. And last one, like this. So there is no convergence. Yeah, so since the terms oscillate between 1 and negative 1 infinitely often, an does not approach any number. So maybe put a space there. Actually remove that. So thus what we have is a limit as n approaches infinity of negative 1, and this does not exist. There's no limit. Does not exist. Like that. And the sequence right here, negative 1, n is divergent. Alright, so now let's look at another example. That's example 7. That's this right here. And it states, evaluate the limit as n approaches infinity of negative 1 to the power of n. I'm in a negative 1 bracket, power of n, and then divided by n if it exists. Remember, this is alternating between negative and positive. But what we should note is, note what happens when we take the limit of the absolute value of that sequence. Limit as n approaches infinity of the absolute value of negative 1 n over n, and then this equals 2. Well, this is going to be always positive, so in other words, it's not going to alternate from negative 1 to 1, it's just going to be 1. And the bottom is going to be, well, always positive anyways, because it's n is positive integer. So it's going to be negative infinity, like this, limit as n approaches infinity of 1 over n. And this one we already know, this 1 over infinity approaches 0. So we already know that, so thus we can just apply theorem 2. So thus, from theorem 2, we have, and if you just scroll up to theorem 2, remember that's just an absolute value. If it equals to 0, then the non-absolute value is also 0. So here's theorem 2. If limit of an, the absolute value of an as n approaches 0 is equal to 0, then the limit as n approaches infinity of an is also equal to 0. So yes. Yeah, so thus, let's just scroll down here. Thus what we have is the limit without the absolute value sign is also equal to 0. So limit as n approaches infinity of negative 1 power of n over n is equal to 0. So yes, very good use of the theorem, which again I'll prove at the end of this chapter, or this section, in exercise 2, I believe. And now this can also be seen graphically, this sequence, and we can see that by, let's put a graph like this. If this is n, this is an, and let's say it goes from, well, we know that if we plug in 1 inside here, we're going to have a negative 1, and then divided by 1. That's going to be negative 1. So we're going to start off at the bottom over here. Just move this up a bit. So this is negative 1. This is where we start. That's at 1. At 1, we're going to have it over here. So that is going to be negative 1 there. And then at 2, well, we're going to have, 2, if we scroll up here, it's going to be negative 1 power of 2 is 1, and then divided by 2. So we'll have 1/2. So this is 1. So we'll have 1/2 over there. That's going to be right over there. And then there's the 3. 3 is going to be, well, a third, but it's going to be negative. And it's going to go over there. And then there's the 4. A 4 is going to be a fourth. And that's going to be a positive because it's even. So it goes somewhere over there. And then as you can see, we can keep going on and on. And it just gets smaller and smaller. This will be over here. This will be over there. This will be across there. And as you see, the limit is going to get, well, smaller and smaller, approach 0.